normally this sort of stuff isn't recorded, but guess if you want. Okay, in project 2, because the stuff was written on the corner of the chalkboard back in the day, and it was done within 5 minutes. So now these are all recorded. Okay, and so project 2 will involve a report and also a presentation on the very last day of class. What you'll be doing with project 2 will be computing the flame structure of a propellant. And so I go into the details of basically how this works and basically how you can do this. But essentially what you'll be computing is the gas phase flame structure of a propellant that is burning using a very detailed chemical reaction mechanism. And this configuration in the gas phase is called a burner stabilized flame. Essentially you can integrate this burner stabilized flame configuration directly with Cantera. You just need to feed it the surface temperature of the burner. And from the point of view of the gases in the gas phase region, the surface of the propellant is like a burner surface because it is basically pyrolyzing or vaporizing, and you know from working with the jump conditions at an interface that there is a blowing velocity, and so basically the surface of the propellant is basically blowing very reactive gases into the gas phase zone, which then react and burn to at least for one of your propellants will produce a temperature profile basically not unlike this right here. And so what keeps the propellant burning is actually heat conduction due to the sharp temperature gradient at the interface, and that keeps the energy either boiling the very top layer of fluid, if it's say nitromethane, or providing the energy that's needed to drive the pyrolysis reactions near the surface of the propellant. And so I go in how to do that. And then essentially what you guys will be doing is there will be 2 different propellants. Basically, group 1, and I'll determine who group 1 is later, they will work with a fictitious double base homogeneous propellant that consists of a mixture of different ingredients. And in the references in this document, they describe how to basically mix those. And also, we have a surface pyrolysis law that you can use. And in the documents that I cite here, they tell you how to predict the pyrolysis species, that is the composition of the reactive gases coming off of the surface. Typically, essentially group 1 will probably be groups with 4 students. I'll decide that. But because you are presenting this, I do want at least 2 different propellants modeled. Otherwise, we'll have 2 or 3 of the exact same presentation on the last day of class. And then basically groups 2 and possibly 3, because I don't know how many students are left in this class. So groups with 3 students will typically model nitromethane. And so this here, it's a different propellant. And you can find the inputs for that you need in a detailed PhD thesis and also a paper. And so basically, these you just have to basically use Cantera to basically integrate this, and then you know the problem is solved once the once the heat flux is balanced at this interface. Because you don't know m dot double prime. You can't find it algebraically like you do for a Chapman-Jagay detonation. And so the burning mass flux, or the burning rate of the propellant, is now an eigenvalue, and you need to sort of guess that, and then check if the heat flux is balanced at the surface. Because basically, once you get m dot double prime, you can estimate the surface temperature. Once you estimate the surface temperature, you can estimate the pyrolysis species. Then you use Cantera to solve the so-called burner stabilized flame. Then you can compute the heat feedback to the propellant. and then check and see if the energy is properly balanced. If they're balanced, you have the correct burning mass flux for that given a state of reactance, pressure, temperature, etc. If they're not in balance, then you need to guess again on the burning mass flux. Okay, and so both of these projects involve actually solving eigenvalue problems, and they involve applying matching conditions based on the solution to a system of differential equations. It's just in project one, the differential equations are fairly simple, so you'll be implementing them yourselves. In project two, they are very complicated, very finicky, and so you'll be using Cantera to solve them for you. Okay, so I suggest you read through this. I know I could, then I'll answer questions on Friday if you have any questions, because right now you probably have 10,000 questions, but you haven't even read through the document. So, and a lot of them will be answered by just reading through the document. Okay, but are there any programmatic questions?
Professor, I have a question. So on the syllabus, there's computer projects, and then there's two of them. So this is the computer projects, I'm assuming.
Yep.
And then there's also just project. What is that, and when do you think we'll start having to work on that?
Yeah, I may can that. I'm not sure yet. That was going to be just a lit review type, a lit review survey, a lit review survey of your choosing.
Oh, okay.
Yeah, it was going to be something along those lines, because we're talking about a whole lot of things, and some of you may be interested in, say, supercritical rocket combustion and going into detail on that. And so you might want to, that'd give you a chance to sort of get credit for reviewing some of those papers. And typically, what was, and if I decide to do that one, again, those ones, you can usually procrastinate those until the last day or two and then basically crank them out. Typically, what I would do, what was done to me is that basically, since the topics are so wide in variety for this type of class, is that you can choose any topic you want that makes sense with energetic materials and multi-phase combustion. It just can't be a topic that is directly related to your PhD thesis. In other words, you have to learn something new. You can't just basically give me chapter one of your PhD thesis and then call it a day. Okay, so are there any questions with that?
And so just one last question. Are you going to be selecting the groups for both projects, or do you want us to form groups?
You guys can form your own groups.
So these super programmers are going to make themselves known, and then we'll split up into those guys?
Yeah. They're Jacob and Braden.
Okay.
Yeah, they are both extremely experienced with Python. And so what I don't want to happen is a super group to form of all four, super programmers, and then a team of only people who have very limited experience with Python. This would be a unmitigated disaster if that were to happen. Okay, does that make sense?
Yeah, that sounds good. Thanks.
Professor, kind of another thing about the groups. How do we know who's still in this class? Because one of my friends was in this class and then he dropped it, but he's still in the Canvas page.
Yeah, I don't know myself. That's sort of why I don't know. There might be 2 or 3 groups. I don't know because I don't know myself either. With this type of class, I expect there to be about a third of the students to drop, and so far that's sort of what happened. Because typically this type of class tends to be a lot more theoretical than some of the much more applied people want. So then it's not what they expected, so they wind up dropping. That's perfectly normal. But I don't know who those people are, and so I can have a guesstimate based on. I think I know one of them that definitely dropped is based on the fact that they didn't turn in homeworks 2 or 3. I can only determine it based on things like that, but I can't discuss with you who that is.
Okay.
because I have no, I wish Canvas was better about doing that. And they may not have formally dropped either. So I don't know. But yeah, I suppose if we send, yeah, if you send, a group text and the person doesn't respond, then they're probably not in the class anymore. Okay. But yeah, but I don't know the direct answer to your question yourself. I've been sort of looking at that myself.
Thank you.
Yeah. Any other questions? Okay. So back to what we were going over. Oops, this calendar needs to go away. So we were discussing the detonation structure in 1D and how to compute that. That's called the Zeldovich, the ZND model, or the Zeldovich von Neumann-Doring model. And basically, essentially what they did is they realized that given the speed of the detonation and the fact that the Chapman-Jagay detonation, the reaction zone are the thing that are the is that it's sort of sonically isolated, so it moves as a unit. So they realized that there's really only one sort of structure that you could have that is steady, and that is if we have a detonation moving to the left, we have reactance here, we have our shock wave that is propagating to the left. That's going to shock, heat, and compress the reactants to the point to where they start to burn. And the point where you have the shock reactants, but no burning yet, that's called the ZND spike. Then after but then basically after a short period of time, due to the massive increase of temperature behind the shock wave, the temperature becomes high enough for the molecules to start to chemically react, and you get a so-called reaction zone. And for the Chapman-Jagay detonation, you have a sonic plane right here, and the sonic plane coincides with the exact point where the burning stops. And so basically what we are after here is we can determine this portion of the structure very easily by just applying, by just knowing what the velocity of the detonation is, and the Chapman-Jagay, and applying the normal shock conditions to jump from this state to the state of the reactants behind the ZND spike. And then what we are doing now is deriving a system of differential equations that you can use to solve for the structure between the shock and the sonic plane. Okay, and so that's basically what we are doing here. And so I sort of went through that. And we assumed in deriving our equations here that the flow is steady, there's no wall friction, there's no heat loss. We are 1D planar, there's no curvature of the shock. We will on Friday start correcting for that. And also in your project 1, you will be basically dealing with that. And the duct that the detonation is propagating in has constant area. And there's also no reactions in the shock itself. So the composition of the gases or the material behind the shock wave or immediately behind the shock wave is identical to the composition of the material in front of the shock wave. Okay, because if you're just barely behind the shock yet, the reactant material has not had enough time to start burning yet. Okay, it starts burning a little bit after the shock. Okay, and so basically what we'll do here is derive a system of governing or of differential equations that you can use to basically start integrating from the post-shock state here and integrate in this direction here towards the equilibrium Hugoniot. Okay, and then if you want to complete the structure, you can basically patch on the reactant state in front of the shock wave there. Okay, and so are there any questions as to where we're going with this?
I just have a quick question real quick.
Yeah.
So the assumption of no wall friction, how accurate is that in terms of, the development of a boundary layer Obviously, this is moving at a really high speed.
There is actually in one of the references that I said are freely available, they actually discuss that effect. It's actually fairly interesting. It's normally pretty small, just because as you said, the detonation moves very fast. And also this reaction zone length here is typically very thin.
Hmm.
So if there's a boundary layer that forms, it's only in this sort of teensy weensy little portion way down here.
Okay. that
Okay,
makes
and so
sense.
basically this here for most detonations is the effect that is the portion that is affected by the boundary layer. And basically, even though it's sonically isolated here, and there's a shock here, so this reaction zone here is sonically isolated, but this boundary layer is starting from the shock itself. And so it's occurring inside of the detonation. And so this sort of boundary layer region does affect the detonation. And typically what happens with the DCJ stuff, I think you wind up with a curve if there's friction. You'll wind up with a curve that'll look something like this. Basically based on the strength of the friction or the height of the channel, something like that. Now, where this wall friction would be important is if you have a very thin channel. Now, if I were to redraw the shock and reaction zone, our boundary layers would look something like this. And then they would actually have time to meet up. And so in this case, a huge portion of the detonation reaction zone is being affected by those boundary layers. And so that effect, and so for a very small system, that would, you could potentially have to worry about that. Does that answer your question?
Yes, it does. Thank you.
And it's the same thing for basically wall heat transfer too, is that basically if you have wall heat transfer, the only way it can affect the detonation is if it has a substantial influence on the reaction zone itself, because any heat that is added after the reaction zone is not going to affect the detonation. Okay? Because again, it has this very, very small chance, because these things move for gases, again, on the order of about 1.5 to 2.5 kilometers per second. For high explosives on the order of 7 to 9 kilometers per second. And these reaction zones for gases are no more than a millimeter, and for explosives can be on the order of a few tens of micrometers. So these distances here are very small. So there's a very, very small chance for heat transfer and wall friction to really affect the detonation, unless you are looking at extremely small length scales. Then it can, or the friction is obscenely large.
One other question, if you're done with that one. Is that one answered? Sorry, I may have jumped in.
No, that's
Go
answered.
ahead.
When you're calculating the strength of that normal shock, are you looking at the sound speed of the non-moving material? So because the temperature is much lower, because we're saying that the detonation is sonic in the reacted area or as it's reacting, but in front of it, you've got non-moving material at some low temperature in comparison. So if I want to calculate the Mach number, would I calculate the Mach number using that unreacted material for that pressure jump?
Yes, so you would base the shock jumps off of the cold reactant state.
So that low temperature versus the velocity of the front. So
yes, and then for now, what we're doing is we are in the shock attached frame. So here we are assuming that the shock is stationary and the flow is being fed in at the DCJ velocity or the detonation velocity rather. Okay, so here you can directly use the shock relations from like your gas dynamics, or if it's ideal gas with constant properties from the tables or the compressible from the tables or the basic formulas that were derived in gas dynamics. Now, if the detonation is moving, then you need to apply the relations for a moving shock wave, which they are the same. You just need to apply a Galilean coordinate transformation from to basically transition from the moving frame of reference to the stationary frame of reference. Okay, and so, but again, it's still just the Rankine-Hugoniot, but either way, it's still just the shock jump. It's just the shock jump conditions, and the state 0 or state 1, whatever you want to call it, is based on the state of the cold reactants, and the Mach number of the shock is based on the cold reactants. Does that answer your question?
Yeah, it does. Thanks.
Okay, are there any other questions? Okay, so we were deriving equations to describe the flow in this region here, and we did conservation of mass, and we showed that basically the mass flux is constant. We worked with conservation of species mass to show that the spatial gradient of the mass fraction is equal to the mass rate of production divided by the mass flux. And recall that the mass flux is just a constant. So this here is just a constant. Or what you'll see in the detonation or in the explosive literature is they will have, they will basically lump these two terms into a sort of quasi mass rate of production divided by the density. Sort of, it's not a mass rate of production anymore. It's sort of a mass fraction change chemical reaction. And then basically they just divide this by U. And so you just need to get used to seeing it both ways. Okay. Momentum, we were working with that. And so we have 1D momentum. So we have just the equation here. We're assuming it's steady, and we're assuming that there's no viscous stress. So we are left with just this equation here. And because the flow, we are only dealing with the flow behind the shock wave, that is guaranteed to be smooth. So we can safely use the product rule here. And we can split this term up into rho u times du dx plus u times d rho u dx. And then this here is nothing more than conservation of mass, and that's not because it's steady, that's conservation of mass. Okay, and so that's conservation of mass. So that term goes away, and what we are left with conservation of momentum is this expression here. Okay, so we have u du dx plus 1 over rho dp dx is equal to 0. Okay, so we work with momentum, and now we work with energy, where we have the time derivative of the total energy. Again, that goes away because it's steady. We have the total enthalpy flux here. We can't do anything with that one yet. We have no viscous stress, so the shear work goes to 0, and we have no heat flux because we are assuming no gradients in the flow, and we're just neglecting it. I suppose, yeah. And then so that goes away because we're just neglecting it. And what we wind up with is that the flux of the total enthalpy is constant. That is, it's the same behind the shock as it is that the flux of enthalpy is the same over here as it is over here in the fully reacted state. Okay. And again, are we in this expression here or in this expression here, does the enthalpy include the enthalpy of formation or not?
It doesn't.
It does.
It does.
Yes, if.
Oh yeah, because it's not equal to anything. That's right.
Yep, exactly. Yeah, sort of one thing is, yeah, you need to get used to sort of recognizing that very fast, because a lot of folks will just list the governing equations, and it'll be incumbent on you to determine whether they include the enthalpy of formation or not. And so you'll sort of have to look at things like this to basically tell. That's part of why if you work with combustion like this, you'll get good at recognizing the various equations because there are so many different forms of them. And they're not always explicit about which ones they are using, so you need to infer yourself. Okay, but again, the flow is smooth, so we can use the product rule here. And if you do that, you go through the exact same steps. You have conservation of mass here times the total enthalpy. This term goes bye-bye because conservation of mass, because the mass flux is constant. And so we are left with just basically this term here. But rho u is a constant non-zero term. So what conservation of energy turns into is that the flow of total enthalpy is constant. Okay, and so that's a very sort of simple looking equation here. Now, typically when we solve these ODEs, we don't work in terms of total enthalpy. And so we are going to split the total enthalpy into just the sort of thermodynamic enthalpy plus the kinetic energy. Okay, so we're going to take this definition here and stuff it into this derivative here, and then expand it out. Okay, so we have the derivative of the total enthalpy is equal to the derivative of just the normal enthalpy plus 1/2 times the derivative of u squared. Well, you can again use the chain rule on this u squared term here, and this derivative turns into dh dx plus u du dx. So our equation here is dh dx plus u du dx is equal to 0. So now what we're trying to do here is right now these equations here are very nice to work with, even work with, say, yeah, these equations here are nice to work with if you're working in terms of the conserved variables, that is the total enthalpy, mass flux, and momentum flux. But what we're trying to do here is we're going to transform these equations here into versions in terms of you can explicitly find the dp dx and d rho dx and du dx explicitly by themselves. And so if we can do that, we don't need the equation of state quite as much. I mean, you still need it, but the system sometimes becomes a bit simpler to integrate. And also you learn a lot more by doing that. Okay. And so what we're going to do here is we're going to take our system of d rho u dx, d rho u squared, dx, dht, dx, etc., and basically transform them into d rho, dx, du, dx, and dp, dx. Okay. And so we need to start working. So the first place to start doing that is we need to start working with the enthalpy equation here. But recall, we can cast this in terms of pressure, because recall when we worked with momentum that we had u du dx plus 1 over rho dp dx was equal to 0. Well, we can solve this for u du dx, and then I'm going to make that substitution and stuff it into here, and that equals so if we substitute that in, we have u du dx is equal to minus 1 over rho dp dx, and then we basically substitute that into here, and then we have dh dx minus 1 over rho dp dx is equal to 0, or the spatial gradient of the enthalpy is equal to 1 over rho times the spatial gradient of the pressure. Okay, so now we go back to our lovely thermodynamics, which you guys love so much in the first portion of this class. But now we want to take this enthalpy and then convert it into gradients of pressure, density, and mass fraction. And so we can assume that density here is, that the enthalpy is a function of pressure, density, and mass fraction. You could choose any two variables here that you wanted. It's usually traditional to use temperature, but for this particular system, it is more straightforward actually to work with it in terms of pressure and density. Okay. So now we're going to take this, function, this functional relationship for enthalpy and stick it into here. And first, as we did before, we got to use the chain rule on this expression here. So we have dH dx equals partial h partial p at constant density and mass fraction times dP dx plus dP. That's a really bad row, Ryan. It looked like delta, for the love of God. dH partial h partial rho at constant pressure and composition times d rho dx plus, and since we can have n species, we basically need to sum up all the species contributions. So we have partial h partial yi at constant density, and constant all mass fractions except for I, times dyi dx. Well, so this here is, we've been using this sort of chain rule here basically several times in this class. And so, but now we can actually start to work with it. So we know what we want here is to get rid of dH dx here. Well, first we know that dH dx is equal, by just based on the governing equations here, no equation of state things. We know that dH dx is just nothing more than basically 1 over rho times dP dx. So we can take that and substitute it into here. And also we know what dyi dx here, or we know what dyi dx is, and we can get that from the species mass, and dyi dx is nothing more than basically either one of these two terms here, depending on which way you want to look at it. Okay, the gas phase combustion folks use this one, and the explosive folks, like say Scott Stewart, they tend to use this one. Okay, and so, but we basically know what that is in terms of the chemical reactions. So we're going to take that and substitute it in. And so here I'm using a cap omega dot over U, so I'm using the sort of explosive style nomenclature, but it's 6 of one, half a dozen of the other. Okay, so I'm going to substitute that into here. And then notice here, if I make this substitution, I have a dP dx here and the dP dx here. And so I'm going to move this dP dx over to this side and this d rho dx over to this side too. Okay. So then collecting like terms, I have 1 over rho minus partial h partial p at constant rho and constant composition times dP dx minus partial h partial rho at constant pressure and composition times d rho dx is equal to basically the sum of basically this term here applied to all the species. Okay, so I'm going to divide both sides by this term right here, and it's going to explode into what looks like a gigantic mess. Okay, so I'm going to divide both sides by this term here. And so I have dP dx by itself. Then I have this really nasty mess of partial derivatives here times d rho dx. And I have this sum here divided by a slightly less nasty a mess of partial derivatives. However, this does not look like it, but you can apply some thermodynamics magic with Maxwell's relations and show that this god-awful mess here is nothing more than the speed of sound squared. Okay, so even though this looks really nasty, we have actually greatly simplified the equation. And then basically here, we almost have the speed of sound, but we do not have this numerator here. And so this term here is just the speed of sound squared divided by this partial derivative, or basically what is left over from there. Okay, and so this equation here turns into something that looks a little less intimidating. We have dp dx minus the sound speed squared times d rho dx. And that's equal to the speed of sound squared. That came from this term over here, over u, times this sort of mess of partial derivatives here. And so this here is just the numerator. And you can show that that basically this partial derivative here, partial h, partial rho, at constant pressure and chemical composition, is the constant pressure specific, or minus the constant pressure specific heat divided by the density, and divided by the thermal expansion coefficient. Okay, and so even though this derivative here looks nasty, it can be computed in terms of properties that you know and are familiar with. So basically, the specific heat, the density, and the thermal expansion coefficient, which for an ideal gas alpha T equals 1 over T. Okay. So are there any questions with that? Okay. So we basically make this substitution into here, and we wind up with this governing equation here, dp dx minus c squared d rho dx is equal to rho over u times c squared times this term over here, which is minus the thermal expansion coefficient divided by Cp times this partial derivative right here times omega dot I. This term here is actually called the thermicity in the detonation literature, and it's given the signal either sigma dot or phi or cap phi. I'm going to use sigma dot. Okay, and sigma dot, or the thermicity, is equal to c squared times the sum of the thermicity coefficients sigma I times the sort of change of mass fraction of species I. Okay, and the thermicity coefficient for species I is equal to minus of the thermal expansion coefficient for the gas mixture divided by Cp for the gas mixture times this partial derivative right here. And if you need the thermal expansion coefficient, and actually there's a mistake, minus the thermal expansion coefficient for any gas is given by this definition here. It's minus 1 over rho times the partial derivative of density with respect to temperature at constant pressure and chemical composition. Okay, and so are there any questions with this? And so we have our new term here, thermicity. And so for those of you who have been through gas dynamics, you've probably seen this expression here before, but it was set equal to 0. And so you can see that if we have zero thermicity, that means we have zero. That means that the rate of chemical reaction is 0. So if we have 0 thermicity, that means our system is inert. And so it makes sense that if we have no chemical reactions, the flow behind the shock just turns into what you would have in a traditional gas dynamic flow. Okay, and so that sort of makes sense. So are there any questions with this so far? Okay, and so I'll have a little homework problem on this, but for a constant property ideal gas with a single chemical reaction of the reactions or of just the reactants going to the products, you can show that basically the pressure will be equal to gamma minus 1 times rho E, and the internal energy will be equal to P over rho divided by gamma minus 1 times the product mass fraction, or 1 minus the species mass fraction, times the density, times the heat of reaction. on a mass basis. Okay, and then using this, you can show that the thermicity is equal to gamma minus 1 times the heat of reaction times the chemical reaction rate. Okay, and so, and gamma is Cp over Cv. Okay, so you can show that all these nasty derivatives that for an ideal gas with constant properties basically becomes a fairly nice expression. So all you need to complete it is a chemical reaction model. Okay, and so why this thermicity is important is, as what I kind of implied up here sort of very subtly, is that if the thermicity is 0, you get a normal gas dynamic flow. But if it's non-zero, you get there is going to be significant influence of chemical reactions on the gas dynamic flow. And so the entire coupling between the flow and the chemical reaction occurs in this thermicity term. So for the flow behind the shock, this thermicity term is actually very important in describing how the flow accelerates or decelerates and things like that. And so if the thermicity is greater than 0, the chemical reactions are exothermic. And if the thermicity is less than 0, the chemical reactions are basically endothermic. Okay, so are there any questions on that? Okay, and so what we can do is we can take this thermicity here, wherever I have its definition, and we can basically write it another way. I'm not going to go through the precise derivation of this, but you can basically split up the sort of two terms here, and you can say that the thermicity coefficient is equal to -1 over rho partial yi times the chemical reaction rate minus alpha over T divided by Cp times this partial derivative right here times the chemical times the chemical reaction rate. And so there are two terms to it in reality, and these two terms here have two different physical significances. And so this term here just involves a change of is a fractional change of density due to because you got this you got this d rho over rho, so it's a fractional change of density divided by the change of mass fraction, and times the rate of change of that particular mass fraction. And so what this term represents is it is the coupling between the reaction of the flow due to changes of basically due to changes of the mixture density due to chemical reaction itself. So to understand this term, you could say you have a solid detonation and your reactant is a very high dense solid and your product is a low density gas. And so basically for that, as you change the solid reactants to the gaseous products, you're going to have a massive change of the density, even if the enthalpy of formation and specific heats of the solid and the gas basically were identical. You would still have an enormous thermicity here, and that's just due to the basically change of the change of density between the reactants and the products. And this term here is basically what you'd normally think of as the traditional heating term. That as you have an exothermic chemical reaction, that's going to increase the temperature, and the increased temperature is also going to drive the density down, which is going to expand the flow and accelerate it behind the shock wave. Okay, so are there any questions with this? Any questions with the project? Again, I would start to form teams. If you can't find the team, contact me and I will assign a team to you. And probably let me know who the teams are by probably Monday. So I'll give you the weekend to sort of sort this out. Let me know who the teams are, and if you need, and then if you if you don't have, if you're not on a team, I will assign you to a team. Okay. So are there any questions on this or the project? Okay.
Thank you.
Yep. Have a good day.
All right, thank you, Professor.
Thank you, Professor.